spin. Goes up real sweet.
Okay.
I actually think I love how she's not helpful. She's like, you're doing great. I'm like, I am certainly not.
Alright, here we go.
I'm like,
What? I rebel against starting early. No, I'm just kidding.
so does Jack.
Yeah, that's right. Jack, you had a question.
Do I have a question?
You had one, right?
I had a question.
Yes, what was it? I can't remember.
It was, how do you tell, like, when you're looking at a graph, tangent, what the, like, how it shrinks or?
Right. Okay. So, tangent, cotangent, secant, cosecant, actually, as we learned today, don't have amplitude. So amplitude is just a feature of sine and cosine. Okay, amplitude is just talking about here's a middle, here's how high the graph goes, how low the graph goes, that's the amplitude. Okay? But really what amplitude is, a vertical stretch or shrink, right, of the graph. Okay? But for sine and cosine, I mean, a special word amplitude. It's really a vertical stretch or shrink. So tangent, cotangent, those have vertical stretch or shrink. So yesterday I was telling you in the homework on those last ones just to describe or list, right, the vertical. So what we want to do is if there's a 2 in front of tangent, we'll just say, so like on our next test, if we have a box like that, which we probably will with the other trig functions in there too, instead of calling that amplitude, we'll just say that's a vertical stretch of 2. Right? If it's a 1/2 in front, we'll say it's a vertical shrink 1/2. Does that make sense? So we'll just describe that as vertical stretch or vertical shrink. Okay, so how do you tell? And let's see, I'm on the wrong one here. Get to our tangent graph. So here's our tangent graph. So yesterday I said that this point right here, so here's one cycle, one branch of the tangent curve. It goes from negative pi halves to pi halves, so that's a distance of pi, so the period is pi for tangent, cotangent. Right in between here, so we said tangent still has these important 4 marks, right? So we still, if we're going to graph a tangent graph, I would still go boom, 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 make those marks. I would put the period over here, which is pi. This would be pi halves. This would be pi fourths. I know I'm rewriting stuff that's already there, but anyway, you know, so this is how you would be doing it by hand. You would write that out, and then you would say, okay, now wait a minute. Tangent, the normal, you have to memorize, right? The normal tangent graph. Just like you had to memorize the normal sine and the normal cosine. Now, those are easy. Sine's at the origin, goes up. Cosine starts up high, goes down. You're going to have to remember the tangent goes through the origin, goes up and to the right, and it's got its asymptotes around the y-axis at negative pi has a pi axis. You're going to have to remember that. Okay? So you'll say, okay, here's my important 4 marks. I know this one in the middle is the asymptote. That's because I've memorized what the normal tangent looks like. And then I know this one starts here. And then this is the key, Jack, to your question. This one in the middle, this first mark, that is at 1. And this point right down here is at negative 1. Sorry. Does that make sense? So if it's been stretched, where are those points? If it's been stretched to 2, where are those points going to be? They'll be at 2. So if this has been stretched, this point in the middle will be at 2. And this point in the middle here, between, when I say in the middle, between the asymptote and the origin, is going to be stretched out. That's the point you're looking for. Okay, so if we do a matching kind of thing, and you're looking at a tangent graph, you're going to want to look where the asymptotes are. Because remember, if you shift this way, the asymptotes have to go with it, right? Those asymptotes have to go with it. If you shift this graph, you shift this red graph, the asymptotes go with it as well. Okay, so if you shift that pi halves, you're going to end up with this asymptote being here, and then this one being a pi, and so forth. Okay? All right, but again, your period, get your period first, like we always do. Remember, it's pi divided by that number now, not 2 pi. It's always the normal period divided by b, that number in there. So tangent, cotangent, the period's pi. For the others, it's all 2 pi. Okay? So get your period, get the 4 marks. No, the asymptote always goes in the middle one, so 1, 2, 3, 4. So you get over here for tangent if it hasn't been shifted, right? But we do the shift later. So we get our period, whatever that would be. We get the asymptote in the middle. We get our stretch number here, and then same thing over here. And then if we need to shift it, then we shift it, right? Just like we do with sine and cosine. So we're not going to spend as much time on these graphs. Number one, they're not as important, and we don't encounter them near as much. And number two, it's pretty much the same. If you memorize the basic shape, then the rest of it is pretty much the same. Okay, so just to look at this, so here is 2 tangent, and so sure enough, this point that was here at 1 is up there at 2. And this one that was down, was at -1, is now down here at -2. Make sense? Okay, all right. So, I don't know, and then cotangent, again, we just have to memorize the basic cotangent graph. Again, if I'm graphing cotangent, I know the period is pi, so I'm going to come in here and start at 0 and go 1, 2, 3, 4, and that's going to be pi, and that's going to be pi halves. The difference here is now I've memorized that cotangent, the normal cotangent has asymptote right on the y-axis and over there at pi, and I know cotangent goes down and to the right instead of up and to the right. But otherwise, same thing. Here, that point's at 1, that point's at 1. Okay? All right. They just kind of draw kind of a smooth curve. All right. Any other questions on the homework then? Do you want to see? Yeah.
Did you ever answer how the Infinite Hotel was?
Yes, thank you. So, the Infinity Hotel, you had an infinite number of rooms, right? And it was full. One person wanted a room. We said, yep, we can make it happen. How do they make it happen?
Infinite amount of rooms.
Right.
So there's always room open.
There's not though. Every room has somebody in it. Every single room, no matter where you go. You pick a number.
It's not infinity.
Room, it is too. Pick any number you want. 2,374,000 room. Go to that room, and there's somebody in it. Every single room, any number you want to name. Google +1. Any number you want to name. There is somebody in that room. It's full. Infinite number. Now, but here's what you got to understand. There are different sizes of infinity. What's 2 times infinity?
2-finity.
No, it's infinity. It's infinity. Again, infinity's not a number, and this is what's crazy about it. This is what's kind of mind-boggling about this whole problem, is it points out this concept of infinity is a hard concept to grasp. So, you've got, every room is full, and there's an infinite number of rooms. Somebody wants a room. One more person plus infinity is still infinity. We should be able to fit them in. So guess what? We can fit them in. Here's how. They get on the intercom. Now, it's not the greatest hotel to stay at, because this is kind of a pain right here, if it's ever full. Because they get on the PA, the intercom, they say, hey, everybody, we need you to pack your bags, pack everything up. We need everybody to move to a room that's 1 bigger than the room you're in now.
But they're all full.
I know, but yes, they can. Tell me, is it possible? If I'm in room 1017, where do I go? 1018, which is fine, because the person in 1018 is going to 1019. Every person's in a room with a number, and every person can move 1 door down, and that room will be empty, because the person there is moving 1 door down. Every single person will be able to move down 1 room.
So like, could the
And
first
so-
person go to the last room?
Yeah.
Well, no. Yes, so everybody does have to move. Okay, great point. Let's just make the first person go to the last room. What's wrong with that? There is no last room.
There is no last room anyway.
There is. I'm saying there's no last room. There's nowhere for that person to go. They would never get there. There's no last room. You're right. There's no last room. There's no last room. Right? There's no last room, but everybody's in a room with a number. Right? Because no matter what number you think of, right? There is no biggest number. We talked about that. I know. That's what's hard. It's infinity. That's what's bizarre. But it is. Every room has somebody in it. It's full. Every room has somebody in it. There's an infinite number of rooms. There's an infinite number of people. Every room has somebody in it. So, what room's open? I know what Jeremiah is saying. He said, so everybody doesn't have to move. Let's just make one person move, right? But the problem is that person can't get there because there is no last room. Everybody moves down one room, so what's open? Room 1 is now open, so that person comes in. Okay? Now, 10 people come and all need rooms. So what do? Everybody get on the PA and they say, hey, everybody move to a room that's 10 bigger than the room you're in, which they can do. Everybody can move down 10 rooms. It would get real annoying and not a great place to stay, but that's beside the point. So now the first 10 rooms are open and they can move into those rooms. Okay, wait a minute. Hasn't even gotten weird yet. Okay, now, there's a convention coming to town.
Yeah.
Track coaches. Infinite number of track coaches.
Oh, that's a lot of track.
I know, it's a lot of track coaches. They need an infinite number of rooms. And the guy says, we're full, but no problem. We can put you in.
Why?
What do they do?
They build a hotel.
Can they do the same thing they did before?
Underground hotel.
Can they do the same thing they did before? They can't. They can't now. It's a problem with Jeremiah. They can't say, okay, everybody move down an infinite number of rooms. What's the problem? They never get there. There's nowhere to go. You can't move from number 1 down an infinite number. You never get there. So they can't do the same thing. But infinity plus infinity is still infinity. So they should be able to fit it.
Sure would be a tragedy if it were to burn down.
Here's how they do it. That fire would never get put out. Firemen we need an infinite number of firemen. All right, listen. What do they do? He gets on the intercom. You ready?
Yeah.
He gets on the intercom and he says, okay, I need everybody to pack up your stuff and you need to move to a room that is double the room you're in now.
Imagine being in room 1000.
Now, I'm not going to lie, if you're in room 1 million, you now have to move to room 2 million. So it might take a while, but you can get there, right? You couldn't move 1 down an infinite number of rooms, so you never get there. But you got to go from room 1 million to room 2 million. It's going to take a while. So they've got like Star Trek, they'll beam you there and whatever. So you can get there, right? But so you can actually get there. There's a place to go.
There is no.
Now, what just happened? What just happened? How did we make room? Well, no, but I mean, how did we make room? Where did all those people go?
To infinity.
No. Come on, now think about it. Room 1 went to room 2. Room 2 went to room 4. Room 3 went to room 6. Room 4 went to room 8. What happened? All the people that were there are now where? In the even numbered rooms. The infinite number of people that were there are now in all the even numbered rooms. So what's open? All the odd numbered rooms. There's an infinite number of odd numbered rooms, and so they all go there. That's what's crazy about infinity. You had an infinite number, it was full, no matter what Seth says, it was full, and as soon as he told everybody to move to a room that's double the one you're in, it was now half full.
I should go into
Right? But you had to still say no to people. Okay.
Where'd you learn that joke, Albert?
It's not really a joke. It was a math class in college, and the professor told it to us. We were talking about infinity and stuff like that.
Person who made it for me.
Okay?
Dude, I should
Now.
go to politics. I'm good at debate.
No, you just got.
I was going to say, I didn't say anything that made any sense. I don't know what you're talking about. All right, listen.
I can't move it down the room. That's cold.
Listen, it's not, because then they moved it. That person was moving too. All right. Now, but here's the problem. Here's the problem is you're too caught up in thinking of the number of numbers and not this idea of infinity. Okay, and that's what makes infinity kind of hard to grasp. Okay, now why? Come on, let's focus back in there. Now, why we care about that? Why we care about infinity? Well, because that's what's happening when we have these asymptotes. As you get close to here, it's undefined, right? Because we get 1 divided by 0 on tangent and cotangent. We do y divided by x, and that's infinity, right? It's not really infinity, but it's tending towards infinity. Now, if you signed up for calculus, you'll get to talk about limits and the idea of infinity. Yesterday we were talking about this right here. We were talking about how 1 divided by 0 is like infinity. It's not equal to infinity, but it's heading to infinity. And likewise, 1 over infinity is is essentially 0. You can think of infinity and 0 as like reciprocals. Not technically, they're not, but you can think of it that way. Because 1 divided by smaller and smaller things is bigger and bigger things. And 1 divided by bigger and bigger things is smaller and smaller things, right? Getting towards 0. So 1 divided by small, think big. 1 divided by big, think small, right? I mean, if you got that concept, that's going to help us with the two graphs we're going to do today, which is secant and cosecant. Okay? So, we got tangent and cotangent, and we'll get some more practice on those, so you'll have a chance to ask more questions about that tomorrow, because you'll have a few more of those in your homework, okay? But we're going to look at secant and cosecant. So, I'm going to start with the sine graph. So, go ahead and just sketch a quick sine graph. Don't worry about all the markings necessarily.
So it's infinity times 0, 1.
Is infinity times 0, 1? No. Is infinity times 0, what would your guess be? What would be the first thing pops in mind if somebody said infinity times 0? Of course it would be 0, because 0 times anything is 0. Well, that's not really true. 0 times anything isn't 0. 0 times any other number is 0, but remember, infinity is not a number. Okay? So, what is 0 times infinity? That's a really good question. It is what we call indeterminate. You need calculus to understand it. Okay? So, sign up. 0 times infinity is indeterminate. 0 times infinity could be 0. 0 times infinity could be infinity. And 0 times infinity could be any number in between. So basically 0 times infinity could be anything. Now, technically, listen, technically we're not talking 0 times infinity, because you can't do times with something that's not a number, anything. Right? And remember, infinity is not a number. So when you say, Noah, when you say 0 times infinity, what mathematically that means is something really, really small times something really, really big. Which isn't, right? Because when you multiply by something big, it tends to want to make the product bigger, right? You multiply by something small, like 1/4, 1/2, 1/3, it wants to make the product, it wants to make the answer smaller. So it's like this battle's going on. Which one wins? Well, it turns out it has to do with how fast the one is getting small versus how fast the one is getting big. Calculus times tone. Okay?
So is negative infinity, is that an actual concept?
Yeah, negative infinity would be like the y-axis if you go down forever. That'd be negative infinity. You go up, that'd be positive.
I thought infinity was like itself would just be all numbers.
It's just big quantity. So negative million, negative billion, that's tends towards negative. Okay? All right, shh. Yeah, you're right. Because when we talk about small and big, we got to be careful. Because negative 1,000,000 is small. Well, it's right, it's less. Well, not really, not what we're talking about. We're talking about size of the number. So for us, negative 1,000,000 would be big, just like million would be big. When we talk about small here, we're talking about towards 0, right? We want to talk about small in value. Okay, so like absolute value, right? So 0. Okay, so back to this. So sine. Now remember, so start with the sine graph. Okay, so sine is 1 over cosecant, right? So we got to start there. Okay, so here's how we're going to quickly, we're not going to plot the values, but or go to the table. But remember we had the table of the sine values? So what we can do is take every one of those and do the reciprocal of it, right? And that would give us our cosecant values. Well, let's just use what we've been talking about to do this. So let's start right here. What is the reciprocal of this y value? This y value is what? 1. What's the reciprocal? 1. That's easy. The cosecant graph is going to be at that very same point. Now, these y values are getting littler. Are you with me? Those y values are getting littler. Like, say, right here, it's like 1/2. What's the reciprocal of that? 2. So that means right here, there's going to be that point. Now, this y value here might have been, I don't know, 0.8. What's the reciprocal of 0.8? 0.8 is 4/5. What's the reciprocal? 5/4, which would be 1.25. So this y value, the reciprocal would be like here, right? Now, look what's happening. These y values are getting smaller and smaller and smaller, closer and closer to 0. What's the reciprocal doing? Getting bigger and bigger and bigger. And then right here at 0, what's the reciprocal of 0? Well, it's undefined, but we said you can think of Infinity, right? The reciprocal 0, but it's undefined. So guess what's going to be there? Vertical asymptote right there, so draw it in. You're going to have a vertical asymptote. Every time the sine graph hits the x-axis, it has a y value of 0. If we do the reciprocal, we're going to be dividing by 0. And so therefore, we're going to have an asymptote. So everywhere, so here's what you're going to do. You're not going to have to memorize a new graph for cosecant. What you're going to memorize is that cosecant is the reciprocal of sine. So you're going to sketch in a quick sine graph. So we're going to do our amplitude, our period, our shifting. We're going to do all that with the sine graph. So if I give you a cosecant graph with a 4 inside and a +1 and a 2 on the outside, you're not going to think of it as cosecant. You're going to think of it as sine. You're going to do all of that like you would if it was sine, and then at the end you're going to do this. What's going to happen over here? These points right here, as these go down, what's the red graph going to do? It's going to go up. And what you're going to get, and what's going to happen over here? Because they're negative, so if you have -1/2, the reciprocal is going to be -2. It's going to be down here. And now these aren't parabolas. Oops, missed that one. These aren't parabolas, but we could call them that. We could call them U's, I guess. They're like U's on the humps. Basically what you're going to have, basically what you remember is this. If you've got amplitude, you got period, you got all that stuff, we're not going to think of it with cosecant. We're going to think of it with sine. We're going to squeeze. We're going to do the new period. We're going to mark our graph. We're going to shift it. We're going to do all that. We'll sketch in our sine graph like you just got done doing on the quiz, and then guess what? We'll come in and we'll draw our asymptotes in here. Now, one thing you got to understand is I said where it hits the x-axis. Remember, if you shift that graph up, it's like your x-axis has changed now, right? And so wherever the middle of the graph is, these points, that's where the asymptote will be. Because if you shift the sine graph up far enough, it won't ever hit the x-axis, right? I mean, if I shift the sine graph up 2 or 3, it's never going to hit the x-axis. So it's always this middle section of the graph. Those points, where they are, that's where the asymptotes go. Okay? All right, and then you just put these parabolas or these U's on top of the humps. And I don't really even care, to be honest with you, about how skinny or, you don't really have to plot any points. The amplitude will get taken care of when you draw your sine graph. If it's up 2, fine. You just stick these U's right on top of the humps. And that is the cosecant graph. So if we look here, okay, I've got my sine graph. See, I've got this sine graph here. Now look at this sine graph I have here. I got a pi force shift. Okay, pi force is right here. So does that look like it shift? Oh yeah, but what's my new period? My period is 2 pi divided by 4. Remember, it's 2 pi, right? 2 pi divided by 4 is pi halves. So I got a period of pi halves. Okay, and this thing is going to shift to the right pi force, but it also has a flip. So what happened is it shifted to the right, but then there was a flip too. So it actually looks like a sine that wasn't flipped. Okay, it wasn't shifted, but that's okay. Fine. Yeah, you see what I mean? Yeah, you're looking at it, you're going, wait a minute, that's not shifted. That's a normal sine graph. Well, it was shifted and then flipped, so it doesn't look like it. Okay, but I wanted to show you what one looked like. So the idea is you would first graph it, just like normal. Graph your sine. And then what are you going to do? You're going to come in and right here, you're going to put an asymptote, right here, right here, right here, and you're going to put the U's on the humps. And that's going to be the cosecant graph. Simple reciprocal idea. Okay? As those sine and as those red values get smaller towards 0, the reciprocal values get bigger. Okay? All right. And then what do you suppose secant's going to look like?
Something similar.
Just with cosine, right? Secant is a reciprocal of cosine. So same thing. Everywhere this crosses. So if we want to graph this one right here, secant, okay? If we want to graph secant, this has got a period 2 pi divided by 2, which would be pi. So we got a period of pi there. We got a shift to the right of pi halves. So it's been shifted over here. There's our cosine shifted over pi halves. Okay, so we would do, so if we're graphing this one right here, we would do it with cosine. all the stuff we already know how to do, and then we would just come in, throw in our asymptotes right there, right? And then we would put in those on top and underneath. And that's it. So secant and cosecant are really easy. You just do just do what you did with sine and cosine and stick those on. Okay? Because they're reciprocal. All right, so it's probably a little more work with tangent, cotangent, memorizing that. Secant and cosecant is really easy. Just add the black stuff at the end. So asymptotes.
Whatever the period is, your, what do you call it again? The dash line. Asymptote.
Asymptote.
That's just gonna go what, halfway through the period?
Wherever it crosses the x-axis.
Yeah.
For cosine.
Yeah, for cosine it's not even halfway through the period. It's where it crosses the x-axis.
Halfway, because if it's pi, and half pi is pi halves, it would be pi. Will be the same for.
The period on this one is pi, right? Halfway through the period is that. It's a fourth of the way, but just where it crosses the x-axis. Just where it crosses the x-axis. Now, the only time that changes is if I shift, look, if I shift this up one, if I do a plus one, it's like your x-axis has shifted now, okay? So if I go plus one here, okay, right, now, here, right, so where do my asymptotes go through? So I've shifted the whole graph up one, but here's my middle, right? Here's that middle of the graph, right, where it goes up and down, right? Here's the middle. That's my new x-axis. So everywhere that is where those asymptotes go, right? So you have the humps nice and centered, you know what I mean? You want to have the humps nice and centered there, you put the U on, right? Just like that. That's where the asymptotes go. I think you're overthinking it as far as where the asymptotes go. Okay? Draw your sine or cosine first. Okay? All right. So just a handful of them today, although, there's more than a handful. But give it a try here. There's just a few out of the book to try to graph. But again, everything starts, the sine and cosine start with those 4 marks. Tangent and cotangent start with those 4 marks. But you just got to memorize what each one is. Now, I'm going to give you a little bit of help. I got 2 things to hand out. This one is not anything to do right now. It's just a picture of all 6 basic graphs. So you can kind of look at this and it'll help you to memorize them a little bit. Okay, tomorrow we'll talk about where it talks about period and domain and range and all that. Okay, so just hang on to this. It's a picture of all 6. This one, we're only doing the side of the worksheet. So it says 6-4B. It's kind of hard to read the B. I didn't write that. I'm blaming somebody else. But the side that has the tangent, the cotangent, the secant, and the cosecant is the side we're doing. Okay, the other side is sine and cosine. Well, we've spent enough time on those right now. We may come back and do that side before our test over this chapter, but we got another thing to do, so we're probably 3 or 4 days away from our test. Probably. Okay, so we have 2 things to do yet. All right, so later next week sometime, probably for a test. Possibly Wednesday. I mean, if you want to plan ahead, probably maybe Wednesday for our test, because we got one thing to do. Start tomorrow a little bit. Monday, Tuesday review. Wednesday maybe.
Write that in your thought. I had a way to get out of this. So you can't do that. Okay,
Yeah. I don't know. I just need to get up something wrong. My life.
I understand that.
I'm gonna be gone tomorrow, is there any other questions?
I don't know how many times I heard that. Yeah. And we actually just had to, so I said, I was like, I
No.
It's
It's gonna be posted out.
Like, yeah.
Just watch the video.